All right, this is our last lecture. And in these first two examples, we're going to look at how we can use differential equations to model population growth. The first example is just a really simplistic model for populations growing under unconstrained conditions. So this could be, this could apply to human population, but it could also apply to deer population or bacteria population, virus population, but we're ignoring any constraints on the population. So we're talking about, unconstrained food supply and unconstrained space, stuff like that, whatever constrains that type of population. So in general, the rate of population growth is proportional to the population, right? So you have more population, you get more reproduction, and so the population under ideal conditions, unconstrained conditions, grows proportionally to the actual population. So we can write that as a differential equation. We can write dp dt is equal to some constant, we'll just call it r, times p. Okay, and it turns out r is essentially the growth rate, right? So we can write r is the growth rate. So if you think about what r has to be, let me get this written here. R, we've got a rate of change, so this dp dt is the population number, the number of whatever population over time, whereas on this side we know that the p is in terms of the population, so this r is essentially like a fraction of the population per time, and so r is the growth rate. And it's also called the constant of proportionality. It's a general term, constant of proportionality. All right. So there's our differential equation, and now if we solve that differential equation, what are we going to get? We're going to separate the variables. We're going to get 1 over p dp is equal to r dt, and then we're going to integrate both sides. When I integrate 1 over p, I get the natural log of p, and on the other side I'm going to get rt and then plus c. All right, so we've done this before. We did this in the last lecture. So p is equal to e to the rt plus c, which we can rewrite as e to the c times e to the rt. Okay, and then I'm going to replace the e to the c here as it's just a constant. So I'm going to write p is equal to a e to the rt. Okay, and so now if we assume that the population p is p0 at t equals 0, then we can substitute that in. We get p0 equals a e to the 0, right? E to the 0 is 1, so that's basically telling us that a is equal to p0, right? So our final equation in terms of p0, which is the initial population, is p is equal to p0 e to the rt, right? Now, this is just exponential growth, right? This is an exponential growth equation. You might also recognize this as being the formula for continuously compounded interest, right? This PERT formula, that's the formula you learn when you learn continuous compounding of interest. And that's just because, the more money you have in an account that's being compounded annually, or compounded continuously, I guess in this case, the amount of money you have, the faster it's going to grow, right? Because it's being compounded at a constant rate, and then it's being reinvested, and then you're earning money on the money that you earned, and so it grows exponentially. So So you may recognize the same formula as being the formula for continuously compounded interest. All right, so that takes care of example 1, and example 2 is a little more complicated model for population growth.